In this notebook, we're going to see how attention heads actually work in a real implementation, not just in theory, but inside a running GPT-2 model. Everything in this notebook is answering two questions. What exactly activates inside GPT-2 when it decides who gets the milk? And once we find that mechanism, can we change its decision? Let's move on with our code. In section 1, we will just be installing our basic libraries and tools that we require for running this. So here the important library is TransformerLens. TransformerLens is the library that allows us to look inside GPT-2 while it is thinking. Normally, GPT-2 is a black box. We give it text and it gives us an answer, but we do not actually know how it arrived there. So TransformerLens allows us to change that. It lets us access internal signals like layers, attention heads, and activations. Without this tool, we would essentially be blind. Fun fact: TransformerLens was created by Neil Nanda, who leads interpretability research at Google DeepMind. Let's move on to section 2. Section 2 is setting up the environment. Here we load the model using something called a hook transformer. A hook transformer allows us to insert hooks. A hook lets us pause the model in the middle of its computation and modify what a specific part of the network is doing. Think of it like freezing time during brain surgery so we can carefully adjust one component. Now let's define our sentences or prompts. So here we'll be defining two prompts. One would be a clean sentence and one would be a corrupted sentence. Let's look at the clean sentence first. The clean sentence goes something like this: When John and Mary went to the store, John gave the milk too. Now, just take a moment and think about who would receive the milk. Will it be Mary or will it be John? Most people would think Mary. Let's find what GPT-2 thinks. So, here GPT-2 is going to measure the model's preference using something called a logit difference. Logit difference is the arithmetic difference between the scores of Mary and John. Think of it like a scoreboard. If the value is positive, then Mary is winning, and if the value is negative, then John is winning. Now let's run the model and see what value the model gives us. Here we can see that, okay, one sec. Here we can see that the value that the first sentence gives us is positive, meaning that the model is going to give you the answer as Mary. You can see the same thing in this chart here. The model is going to give you the answer as Mary. Now let's move on and run the model on our corrupted sentence, where we would be switching the word Mary with this synth keyword here. This is basically a synthetic placeholder word, and this would be a corrupted prompt. And let's run the model on this. Here, as you can see, the model is going to give you a negative result. Now, this means that the model, instead of Mary, the model is going to give you the answer as John. We just switched one word and the entire belief reversed. And you can see the same thing in this chart right here. Now, this brings us to our question. Where inside this 12 layer network does that decision live? So, let's plot our internal activations. Let's run the original sentence again. And this time, we are not just going to collect the output, we are going to record everything with it: every layer, every attention head, and every internal activation. This is like taking a full MRI scan of the model's brain. So now we have a snapshot of what a Mary decision looks like internally. Next, we run a corrupted sentence, like the same corrupted sentence again, and we are going to perform an experiment. We're going to take one attention head at a time and temporarily replace its corrupted activation with the clean activation from the original run. Just one head at a time. If Mary's score increases again, that means this head was carrying important information, meaning that this head was contributing to that decision and was carrying the information that was responsible for this decision. We're going to repeat this process for all 144 attention heads, layer by layer and head by head. So, in order to test our causality, we are going to perform something called an ablation. In simple words, ablation means silencing the head. Formally, it means that we intercept its output and replace it with a neutral static. But we do not set this neutral static to 0 because 0 is itself a meaningful direction in the vector space. And we do not aim to damage the model. We are just carefully muting one component. So, as you can see here, we have muted layer 0 head 1. Then we have further muted 3 of the important heads in order to see if the confidence drops or not. We can see that Mary's confidence has dropped. Initially, the confidence was 3.09 and now it is 1.63. Now, let's perform it again. And we see that the model is still going to give you the answer as Mary, although the confidence has dropped. You can see that here as well. But we aim to gaslight the model completely, meaning that we want it to change its decision. So here we can conclude that although the head was contributing strongly towards the decision Mary, it was not working alone. It was a team effort. So silencing weakens belief, but it does not completely reverse it. This brings us to section 8, which is gaslighting the model. Now, instead of silencing the head, we are going to flip its signal. We multiply its output by minus 1. So if the head previously pushed the model towards Mary, now it is going to push equally toward John. We are not removing the gear, we are simply changing its direction or reversing its direction. Now let's run the model again. As you can see here that the logit difference changed from positive to negative, meaning that we have flipped the logit difference. So now the decision that was initially Mary has become John. So the entire decision reverses. You can see that here as well. This reversal has been done with just one multiplication. There was no retraining involved, no fine tuning, and no prompt engineering or reinforcement learning. Just flipping a single internal signal. Now, this brings us to our obvious question that after all of these experiments that we have performed, did we finally break the model? This is called a sanity check. Now, let's run the model on something completely unrelated. So, there is a control prompt. The cat sat on though. Now, this is not related to any of the prompts that we have given it before. The model predicts the word as floor. Now, the cat sat on the floor is not wrong English. It is not grammatically or syntactically wrong. It is perfect English. Hence, we can say that the system still works normally. So, we have not destroyed the brain at all. We have simply modified one specific circuit. Let's move on to section 10, which is basically about all of the graphs that you had seen before. So, the first graph shows you the healthy brain or the healthy model. That is basically when the model gives you the answer as Mary. The second graph shows you after ablation the that the confidence in decision Mary drops. So as you can see here, it drops from 61.9 to 3.1%. The third graph shows you the gaslighting of the model, where we are forcing the model to give the answer as John. And the fourth graph shows you the control test or the sanity check, where you had tested a completely unrelated sentence that was about that cat which was sitting on the floor, and hence the answer is floor. So, what did we actually learn here? Or what did we actually do in this notebook? We measured the decision margin, we recorded the internal brain activity, located the responsible attention head, silenced it or ablated it, reversed it or flipped the decision, and verified the rest of the model still works or performed the sanity check. This is not correlation. This is intervention and causality. Earlier, circuits were just theoretical diagrams. Now you have seen one as a controllable piece of machinery. Not magic, not mystery, just a mechanism. And once you can flip circuits, you can map them. Once you can map them, you can control them. And suddenly,